as you go through like later on in life and take the ACT your junior year, the science section is largely just interpreting data tables and graphs. Understanding graphs is fairly big. Our book does a pretty decent job of it, I think. Being able to understand what's going on in a graph is really quite important for future stuff. All right, so we're just going to start with interpreting graphs. So interpreting graphs. If you have time as one of your two variables, it's pretty much always going to be on the x-axis. You can get some things that it's not, but pretty much always 90-some% of the time it's going to be on the x-axis. The key to understanding a lot of these graphs is that basically you just look at what happens to y as you go left to right across the graph. So look at what happens to y as you go, I'm just going to do an arrow to the right. So look what happens to y as you go to the right across the graph. Right across the graph. That at least for line graphs, that's going to be a pretty good rule of thumb for interpreting things. So if you have something like this here, just a horizontal line, what's happening to y as you're going left to right? Staying the same. So if you pick, you could even, push comes to shove, just make up numbers even if you have to. Right now that blue line, let's make it green, that line there is going to have a y value of about 7 or 8, something like that. And do you agree that it doesn't change? It stays at that same height, stays at the same y value. So for this, y stays the same. So if you're looking at a graph, you're not totally sure, you could even make up numbers just to give you an idea. But look, is y getting bigger? Is it getting higher? Is it getting lower? My second graph, I'm going to have my line just kind of going upwards slowly. So now we have here y is increases, or y increases slowly. So y increases slowly. If you were to have a line that's looking more like that there, you could say quickly. You're probably not doing multiple colors, so maybe we should even do like a dashed line or something like that. If you have something like that, you have y going up quickly. So quickly would be the dashed, slowly would be the solid, something like that. And then you could do the same thing with a decreasing line. So if you have this here, y decreases. So if you were looking at a graph of speed versus time, whenever they do like a label on a graph, they always talk about the y-axis first. So if these things here were all like speed and time, it's too sloppy to be insanely helpful. But if you had speed and time, the green would be a car that's slowing up slowly, like on our streets this week where we've had all this snow. You're not speeding up real fast, but then you're spinning your tires perhaps, and then you hit pavement, like dry pavement, then you could have more of that red. Your car speeds up quickly. The pavement's dry. But yes? Yeah. So kind of a lame example, but we'll move on. Two other types of graph they're going to look at would be one like this here. And if you could draw the graph without lifting up your pencil, they refer to that as a continuous graph. So a continuous graph. You could do the definition if you want to. It's not really a proper definition, but you could say you don't have to lift pencil. Don't have to lift pencil. The next kind is going to be if you have a bunch of, well, I should back up. So continuous graph would be like if you're looking at like distance versus time. Your car's not going to magically jump from one place to another. Or the length of your hair is getting longer, then they cut it, although the downward would be a lot shorter or a lot quicker down. If you have a different type of graph that's made up of points that aren't connected, they call it a discrete graph. So discrete graph.
How many times are there?
These are going to be unconnected points. That's all we're going to do as far as continuous and discrete for this here. Unconnected points, or you could say you must lift your pencil, getting from one to the next. If I had those going up in a nice straight line, one example that I often use for that would be, actually let me just do my example, so when it comes to mind. So I'm going to say example 1, the only one in the notes. Henry sells cars. He makes, I have absolutely no idea what a car salesman makes. I'm just making these up. But he makes, we'll say, $20,000 a year. Just as like a base pay. And I'm guessing a lot of people that are salesmen do this type of thing if they work on commission, whether it's you're selling houses, you're selling something else. But you get a certain amount a year, and we'll say $500 for each car he sold. So, and $500 for each car sold. So then you could do graph the salary. As a function of number of cars sold. So our salesman makes $20,000 a year and gets an additional $500 for each car he sells. So graph the salary as a function of the number of cars sold. So if we take our graph, first of all, is this, maybe I should back up. You could, if you wanted to, do the broken axis. We talked about that in here, didn't we? I know we did in the Math 8 at least. But they do like the little broken axis. You could say like 0 cars, 1, 2, 3, 4, 5, something like that. And you could make a bigger domain, more x values on there. But how much does he make if he sells 0 cars? 20,000. So the lowest y value, this is just kind of the broken axis, so we're not starting down at 0. But you could say like $20,000 would be here. And if you're ever stuck, you could go the old-fashioned way and just make your data table. And say if he sells 0 cars, this would be cars. And this would be the money. So 0 cars, he's going to get 20,000. If he sells 1 car, he's going to make 20,500. 2 cars would be 21,000, and so on. That you basically, each time x goes up 1, you add 500. So the slope is 500. So every time you go over 1, the rise is 500. But so now we could, for this guy, say, all right, 1 dot then is going to be right here at 0, 20,000. And then maybe if I do like, we'll call that 21, we'll call that 22, so 22,000. So my second dot for 1 car then is going to be halfway between 20,000 and 21,000. So right there. Do I connect the points?
No. Yes. No.
If you argued maybe he works at a junkyard, but if you're like, you're not going to make commission if somebody comes into the car dealership and says, ooh, I really like that Acura. Can I have the hubcaps? And it's like they don't sell part of a car. Either he sells 0 cars, or he sells 1 car, or he sells 2 cars. So this is going to be a discrete graph. In a discrete graph, the points should be in, for this case at least, a straight line. Because every time x goes up by 1, the y value should go up by 500. That's the slope. So something like that. But that would be an example of a discrete graph, where they call it the domain is a limited domain.
Why don't you connect the dots?
Okay, because if you were to connect the dots, that'd be saying there's like a point here. So maybe a point right there.
Where?
Trying to make it show up on my thing. But that there's like, so half of a car would be 20,250. But I'm guessing that his boss isn't going to be happy if, so I'll sell you the back half. Somebody comes in with a cutting torch and takes the back half off. So the domain only makes sense to be whole numbers. So things like that could be, and I should have thought of examples and wrote them down so they're not off the top of my head, but like the number of people that you invite to your birthday party and the cost for food. You know, you can't really invite half of a person to your birthday party. The number of pets you have and your veterinarian bill. But things that can't be decimal answers. So, seem good? Yeah. That's it.